Hello everyone, I'm Norman Wildberger. In this famous math problem, we're looking at how to calculate cyclotomic polynomials. These are an interesting family of polynomials that arise in algebra, and they have a lot of consequences for field theory and Galois theory. So today we're going to be focusing on the notion of irreducibility and an important criterion for irreducibility due to Schoenemann and Eisenstein. Okay, so the cyclotomic polynomials arise when we try to factor 1 minus alpha to the n, where n is a natural number. And here are the first few cyclotomic polynomials. Phi sub 1, which is a little bit different from all the others, that's 1 minus alpha. Phi sub 2 is 1 plus alpha. There's phi sub 3, phi sub 4, phi sub 5, 6, 7, 8, 9, 10, 11, and 12. And the pattern is not at all obvious, but one thing that we do observe is that when we have a prime like 7, then there's a kind of a predictable nature to the cyclotomic polynomial. Same thing for 5, same thing for 3, same thing for 11. Okay, now one of the key features of these cyclotomic polynomials is that they are irreducible. And that means that they can't be factored into a product of polynomials or polynumbers of strictly lesser degrees. So what was our definition of the cyclotomic polynomials or polynumbers? Well, we said that phi sub n was the factor of 1 minus alpha to the n, which is not a factor of the polynumbers 1 minus alpha to the k, where k is a divisor of n and less than n. So if you look at, say, two such polynumbers, let's say 1 minus alpha to the 7 and 1 minus alpha to the 21, okay, 1 minus alpha to the 7 is going to divide 1 minus alpha to the 21 because 7 divides 21. That's a pretty easy consequence of the fact that 1 minus alpha is always a factor of 1 minus alpha to the n. So it follows that any factor of 1 minus alpha to the 7 will also be a factor of 1 minus alpha to the 21. Okay? So what we're doing when we isolate the cyclotomic polynomial this way is we're saying this is the factor that does not arise as a consequence of any smaller polynomials of the same kind. Now, a crucial fact about these things, which is not at all so obvious, is that phi sub n is actually irreducible. And what that means, typically irreducibility is something that's valid once you've chosen a number system. So you choose a number system and then you say, okay, a polynomial in this number system is irreducible if it can't be factored as a product of strictly lesser degree polynomials with coefficients still in that number system. Okay, so usually we like to think about irreducibility in terms of integers, where we're talking about polynomials with integer coefficients, but sometimes it's maybe more convenient to think about polynomials with rational number coefficients. So those two notions of irreducibility might be a little bit different. So let me mention Gauss's lemma, which is a very important sort of elementary result in this direction, but establishes that there's really not much of a distinction between irreducibility over the integers and irreducibility over the rationals when we're talking about polynomials with integer coefficients. So one way of framing Gauss's lemma is that if a monic polynumber with integer coefficients is a product of two monic polynomials with rational coefficients, then in fact all of those rational coefficients have to be integers. So that's the first claim, that these phi sub n, these cyclotomic polynomials, are irreducible. And then in terms of then, we have an answer to the question of how to factor 1 minus alpha to the n. Then 1 minus alpha to the n is the product over all the natural numbers d that divide n of phi sub d. So these are perhaps the two main facts about the cyclotomic polynumbers. So let me illustrate those ideas with an example. Let's have a look at 1 minus alpha to the 24. Now my computer will factor that thing very quickly. So here are the 8 factors of this thing. 1 minus alpha, 1 plus alpha, 1 plus alpha squared, 1 plus alpha squared, 1 minus alpha plus alpha squared, 1 plus alpha to the fourth, 1 minus alpha squared plus alpha to the fourth, and 1 minus alpha to the fourth plus alpha to the 8. And just as we've stated in that second fact, this can be interpreted as a product of all the cyclotomic polynomials, one corresponding to each divisor of 24. So this one here is actually phi sub 1, this is phi sub 2, this is phi sub 3, this is phi sub 4, this one's phi sub 6, this one's phi sub 8, this one's phi sub 12, and the remaining one, the one that we have left over after we've taken out all those factors from the lesser exponents, is phi sub 24. So conclusion, phi sub 24 is 1 minus alpha to the fourth plus alpha to the 8. And now you can kind of see, perhaps, that even with a computer, a powerful computer that's able to factor polynomials or polynumbers very quickly, still finding these cyclotomic polynomials is not going to be that trivial. Because let's say we have a bigger power, maybe 536 instead of 24. So maybe there's going to be lots of factors that our computer can calculate relatively quickly. But in order to identify what the actual cyclotomic polynomial is, we have to have some control, at least from this point of view, of all of the cyclotomic polynomials of all the divisors of that number. Okay, so we have to recognize, that's phi sub 36 and that's phi sub 72 or whatever. And then the one that's left over is the actual cyclotomic polynomial that we're interested in. So that's something that your computer has to be programmed to do. And it involves actually, at least naively, keeping track of all of the cyclotomic polynomials up to the point where we're at. So that becomes computationally quite onerous. But how do we know that this extra factor that we have here actually is irreducible? Now, perhaps our computer will tell us that it is because it's not able to factor it. But how do we really know? That's a very good question. How do we tell whether a given polynumber is irreducible? Not so easy at all. By Gauss's lemma, we can certainly restrict to integral factors. So this is one approach. So let's say we wanted to test by hand whether this thing was irreducible. One way would be to naively say, okay, let's suppose that maybe it's a product of a factor of a polynomial of degree 2 times a polynomial of degree 6. Well, those coefficients of those polynomials have to be integers. And so we could write out what they are, and then we could sort of equate sides and get some conditions on those integers, because after all, the product of those two polynumbers has to be this one here. Right? So in particular, for example, the constant terms, there's not a lot of choice for them, because if the constant term here is a0 and here is b0, we have to have a0 times b0 to equal 1. And if a0 and b0 are integers, well, there's only two possibilities there. Okay? So we could proceed in that direction, but you could imagine that it might be quite a lot of work. So are there any general criteria to check irreducibility? This is a very important practical problem in algebra. Okay, so the first general criterion for irreducibility that I know of was published by Thomas Schoenemann. And here it is. Suppose that f is an integral polynumber, that means it has integral coefficients, of degree n, which is strictly positive, so it's not a constant polynumber. And suppose also that there is a prime p and an integer c, so that you can write the given polynumber in the following way, as a power of alpha minus c. So alpha minus c to the n, where that's the same as the degree of the polynumber. And an additional term, which can be written as the number p, which is prime, times some other polynumber capital F, where, in addition, this capital F satisfies the condition that f evaluated at c is not congruent to 0 mod p. That means it's an integer which is not divisible by the prime p. Then the conclusion is f is irreducible. So this is a check, a criterion that will establish that some polynumber is irreducible. Now, the proof involves some algebra with polynumbers mod p, and actually also mod p squared is involved. It was published in 1846 by Schoenemann in a very important journal at that time called Krell's Journal, which actually is still around, perhaps the oldest continuing journal in the world. Okay, so what's involved here? So we have to do a little bit of shifting from algebra with integers to algebra over this essentially a finite field, a field with p elements. Okay, so basically what you need to know there is that to work with this field of p elements, or mod p, we're setting p equal to 0. So whenever there's a p, let's say p is 7, so whenever you see 7, you can replace it with 0. That means that any multiple of 7 is also 0. So 14, 21, minus 7, they're all equal to 0. So the algebra really simplifies, and you really only have 6, in the case of p equals 7, 6 sort of elements in the field, the integers from 0 to 6. And what's important about this particular number system is that it has a lot of properties of rational numbers. In particular, it's a field, and that means that non-zero elements are invertible. So that has the consequence that when we're working with polynomials or polynumbers, the kind of familiar algebra that we might be used to for polynomials in the integer domain or over the rational numbers are also going to be holding here. And the main thing that we need to appreciate is that unique factorization of polynumbers is still applying when you view things mod p. All right, so let me outline the proof of Schoenemann's theorem. Suppose that our polynumber f can be written as alpha minus c to the n plus p times capital F, where p is a prime and capital F has this property that f of c is not divisible by p. In other words, not congruent to 0 mod p. And let's suppose that this thing is not irreducible. In other words, that it can be factored as a product of two polynumbers, g and h, with, say, the degrees of g and h both being strictly positive. So one of them is not just a constant. We want to derive a contradiction, and then that will establish that f is actually irreducible. Okay, so one way of stating this or restating it in terms of mod p, if we look at both sides mod p, then this thing here, being a multiple of p, is going to be 0. And so we could say that alpha minus c to the n is congruent to product gh mod p. So this triple equality there, that's a congruence equality. That's the sign that we use when we're working mod p. So they're working in this restricted algebra or arithmetic of a finite field with p elements. P is a prime. Okay, so but unique factorization of polynumbers holds mod p. This is a field, and so it has nice properties. So if we look at this thing here, we see, okay, here's a polynumber, here's a factorization of it. But there's essentially only one factorization, at least when you sort of dispense with sort of multiplying by scalars, okay? So the conclusion of that is that g and h actually have to be powers of alpha minus c themselves. So mod p, g should actually be alpha minus c to some power k, and h should also be some power of alpha minus c, say to the L. The sum of k plus L should equal n, so that both sides agree, and k and L should be strictly positive because we're assuming that g and h are not constants. So what can we deduce from this? Well, then clearly, if we plug c into g, we're going to get 0 mod p, because 0 to the k is congruent to 0 mod p. And similarly, h of c is going to be congruent to 0 mod p. So the numbers g of c and h of c are both integers, which are divisible by p, both of them. Okay, so now we go back to say this equation here, and we plug c into f. So f of c, that's going to be 0. We're going to get p times f of c. What do we know about that? Well, that's the same as g of c times h of c. Both g of c and h of c are, we just said, divisible by p. So this product is going to be divisible by p squared. So p times f of c is congruent to 0 mod p squared. And that's a contradiction, because that means that this f of c actually has to be divisible by p. Because here's p times something, which is divisible by p squared, so that something has to be divisible by p. And we assumed that that was not the case. That's a contradiction, contradicting our assumption that f is a product of polynumbers of lesser degree. Conclusion, f is irreducible. And so now, a very important conclusion, which Schoenmann was keen to draw, was that in fact the pth cyclotomic polynumber, phi sub p, which is 1 plus alpha squared all the way up to alpha to the p minus 1, that is irreducible. So let's see why. We are assuming that p is a prime. And so the binomial coefficient p choose k, which has the form p factorial over k factorial times p minus k factorial. That is going to be most of the time congruent to 0 mod p. In other words, it's going to be divisible by p. If the k value here is between 0 and p, so not equal to 0, not equal to p, then both of these terms down here are non-zero. And the factor of p occurs only in the numerator. So that means that this quotient is going to be divisible by p. So for example, if you expand 1 plus alpha to the 7, okay, you're going to get 1 plus 7 alpha, and then there'll be other terms that you get from looking at the 7th row of the Pascal triangle. And if you look at that 7th row, except for the initial one and the final one, all of the other coefficients are divisible by 7. That doesn't happen typically for a general row, but if the row corresponds to a prime value, it does. That's exactly what we're pointing out here. So that has the important consequence that if we expand something like 1 minus alpha to the p, that most of those coefficients are going to be divisible by p. So when we look at them mod p, they're going to be 0. They're going to disappear. And we're only going to get the first term, 1, and the last term, which is minus alpha to the p. Yeah, I guess I should say we're usually working with an odd prime here, but if p was 2, then minus 1 is the same as 1 anyway. Okay, hence, let's look at this cyclotomic polynumber phi sub p. That is 1 minus alpha to the p over 1 minus alpha. That's another form for this geometric series. Okay, but mod p, we can exploit the fact that this 1 minus alpha to the p is actually congruent to 1 minus alpha to the p. So imagine replacing this numerator with 1 minus alpha to the p. Then there will be a cancellation with that denominator, and we'll just get 1 minus alpha to the p minus 1 mod p. So the cyclotomic polynomial phi sub p can be written as 1 minus alpha to the p minus 1 plus something else, which is divisible by p. That's what it means for two things to be congruent mod p. It means that the difference is p times something else. Okay, so there'll be a p times something else. The something else is, say, capital F. Okay, this is looking a lot like the Schoenmann criterion. And what about f of 1? So this is sort of like, the constant c, okay? C is 1. So what is f of 1? Well, what do we know about phi sub p if we sort of plug in 1 into this equation? This will be 0. And phi sub p of 1, what is that? If we plug in alpha equals 1 here, we're going to get 1 plus 1 plus 1 all the way up to here. There's p terms here, so we're going to get a total of p. Okay? So the left-hand side, phi sub p of 1, will be p. This is 0. And here we're going to get p times something. So what is that something? The something has to be 1. So f of 1, capital F of 1, is actually equal to 1. In particular, it's not congruent to 0 mod p. So this thing is irreducible exactly by Schoenmann's criterion. Okay, so that argument's rather abstract. Let's have a look at some concrete examples to reinforce our understanding of that situation. So let's look at a couple of the cyclotomic polynumbers where the number is prime. So phi sub 3 is 1 plus alpha squared. It's of degree 2. So we could write it as phi sub 3 equals alpha minus 1 squared plus something else. And if you do the calculation, the something else is just 3 times alpha. So yes, indeed, this is sort of the situation where the prime p is 3, and this other factor here is indeed not equal to 0 mod 3 when we replace alpha with 1. When p is 5, there's our cyclotomic polynumber, we could write it as alpha minus 1 to the 4th plus something, and you can calculate what that something is. It's 5 times alpha times 1 minus alpha plus alpha squared. So the prime is 5 in this case, and this extra factor here has the property that when you plug in 1, you get 1 times 1, which again is non-zero. And for phi equals 7, we get alpha minus 1 to the 6th plus 7 times 1 minus alpha plus alpha squared, all squared. And the same argument works. When we plug in alpha equals 1, we get 1 there and 1 squared. So we're definitely not getting something divisible by 7. So it already suggests sort of an interesting little question, right? I mean, if you take a larger prime, then something like this should be happening. If you take phi sub p, you write it as alpha minus 1 to the p minus 1. Then there'll be some extra factor that we've sort of exploited. It'll be p times something else. And the question might be, what is that something else? What we're getting here seems to be sort of something, has a little bit of a cyclotomic aspect too. What happens for larger p? That's a kind of exploration that you might want to have some fun with. As another application of Schoenmann's criterion, let's look at a case for a value where we're not having a prime, but say phi sub 9. Phi sub 9 is 1 plus alpha cubed plus alpha to the 6th, and the claim is that that is also irreducible. So if we try to apply the same reasoning, we might try to write it as alpha minus 1 to the 6th, because it's of degree 6, and then there'll be something left over, and we can calculate what that something that's left over is. It's 3 times alpha times 1 minus alpha plus alpha squared times this more curious factor, 2 minus 3 alpha plus 2 alpha squared. So what are we supposed to do? We're supposed to check what happens to this thing when we evaluate it at the constant, which in this case is 1. So if we evaluate it at 1, well, f of 1 is 1. This term is 1 minus 1 plus 1. That's 1. This one is 2 minus 3 plus 2. That's also 1. So altogether we get 1, and that's not congruent to 0 mod 3. Okay, so it's 3, that's the prime, times f, and the f of 1 is not congruent to 0 mod 3. So, by Schoenmann's criteria, phi sub 9 is also irreducible. So we've gone just a little bit beyond purely the prime case. These days, Schoenmann's criterion is often not studied in undergraduate courses. Rather, Eisenstein's criterion is presented. The two are actually quite close to each other, as was pointed out by Schoenmann shortly after Eisenstein published this in 1850, actually in the same journal in which Schoenmann had published his work a few years earlier. Schoenmann pointed out, quite rightly, that Eisenstein's criterion was actually just easy consequence of his. And in fact, they're pretty well equivalent. So let's have a look at Eisenstein's criterion. we're given a Pauli number f explicitly as a0 plus a1 alpha plus all the way up to a sub n alpha to the n. And this is an integral Pauli number, so these are all integer coefficients. And we'll suppose that p is a prime that has three properties satisfied with relation to these coefficients. First of all, p divides a0, a1, all the way up to a sub n minus 1. So all the way up to, but not including, the top coefficient. We'll assume that p actually does not divide the top coefficient a sub n. And finally, that p squared does not divide the lowest coefficient a0. The conclusion is that then f is irreducible. So let's see why this is actually a consequence of Schoenmann's criterion. We'll start by just revamping this polynomial to arrange that a sub n is actually congruent to 1 mod p. We know that a sub n is not divisible by p. And that means that when you're working mod p, it has an inverse. So for example, let's say we were working mod 7 and that this coefficient, this top one, was coefficient 3. Then 3 has an inverse mod 7, namely 5. Because if you multiply 3 times 5, you get 15, which is the same as 1 mod 7, because you can throw away 14. Okay, so if we multiply all coefficients by 5, then we basically have the same Pauli number, as far as irreducibility is concerned. But now we are arranging that this top coefficient is congruent to 1 mod r prime. Okay, so then what we do is we strip one of these alpha to the n's away. Okay, so we take one alpha to the n, put it to the left, and then what's remaining is going to be divisible by p. Because all of the lesser coefficients are divisible by p from our first assumption. And we've just arranged that this a sub n is congruent to 1 mod p, so it's 1 more than a multiple of p. That means if we take one of them away, what will be left will be a multiple of p. So we can write the remainder as p times some f. Now in this case it's like Schoenmann's criterion, with the c value being 0. Okay, so we need to check what is f of 0. We want to show that f of 0 is not congruent to 0 mod p. If you take a polynomial and you plug in 0, you're just getting the constant term, right? So this is just the constant term of f. So what's the constant term of f? Well, p times the constant term of f is a0. But we know from the third criterion that p squared does not divide a0. P divides a0, so we were able to pull a factor of p out of a0, but we're not able to take out another factor of p. So this f of 0, which is what's remaining when you take p out of a0, has to be not congruent to 0 mod p. Okay, well that's exactly the situation where Schoenmann applies. So we conclude that f is irreducible by Schoenmann's criterion. So that's an interesting story. Certainly, Schoenmann deserves at least equal credit to Eisenstein. So from now on, let's call this criterion, or the other one, the Schoenmann-Eisenstein criterion. Spread the fame around a little bit, okay? Now, we are making good progress. We now have control over these cyclotomic polynumbers phi sub p, when p is a prime. But that's still a far cry from the general phi sub n. And how do we know that thing is irreducible? Well, that's actually a knotty question as far as I can see. And there are standard proofs out there in the literature, but I'm afraid that when we look carefully at them, we are meeting some logical difficulties. So we're going to have to talk a little bit about that. It has a lot of influence to modern field theory and Galois theory, what we're going to be mentioning next time. Still in pursuit of trying to understand these cyclotomic polynumbers. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.